Hey, we're going to look at LDRs. So LDR stands for light dependent resistor. So it's a resistor that depends upon the light intensity that is incident upon it. And the symbol you can see here shows that the two arrows represent the light and the little box here represents the resistor. We're going to look first of all at the graph of how light intensity affects resistance. So I'm just going to sketch it here. You'll notice that as the light intensity increases, the resistance goes down. But we need to analyze this a little bit more carefully. So let's look at low light intensities, which I've circled there. The resistance decreases at a rapid rate because LDRs are more sensitive at this point here. That means a small change in light intensity causes a big change in the resistance. If we have a look at this end of the graph at high light intensities, the resistance decreases but at a slower rate, which means that they're less sensitive. So whenever you have to describe this graph, don't just say as light intensity increases, resistance decreases. You say that when light intensity increases, the resistance goes down, but it does so at a decreasing rate. It's really important to talk about rates when we have a curve. The reason why LDRs behave in this way is because they're made of material called a semiconductor. So we're going to go back and just do a quick recap about what we mean by conductors and insulators. So N here stands for number density of free electrons. Conductors have a high number density of free electrons, which means that they conduct electricity very well. Insulators, on the other hand, have a very low number density. Semiconductors, as you might guess, are somewhere in the middle. And when you shine light on them, more intense light, you actually increase the number density of free electrons. Therefore, they're able to conduct better. Higher conductivity means a lower resistance. If you have to describe an experiment to determine this graph, to get these results yourself, you need to set up an experiment as shown over here. So we've got an EMF supply, we have an ammeter, and we in series with the LDR, and we have a voltmeter in parallel with the LDR. And all you then have to do is use the equation resistance is the potential difference divided by the current. You measure the current using the ammeter, the potential difference using the voltmeter. We now need to vary the light intensity, so you need to use some source of light. To vary the light intensity, you can just move this light source. You can start with it close to the LDR, and then you can move it away. As you move that light source away, the light intensity is going to fall. So you measure the resistance, you vary the light intensity, and then you plot your graph. And then you get the trend that we have seen over here. LDRs are really important because they're used in light sensing circuits. So in your mobile phone, there is a light sense which determines the automatic screen brightness level. It also is used to determine whether the flash turns on or off. And it's also used in street lamps to turn them on and off in response to varying light levels in the environment. So they have lots of uses, and we'll look more about how they're used when we do potential divider circuits and light sensing circuits. Thanks for listening. See you all soon.